Okay, so comets, very beautiful things. How do they fit in the creation model? But before I get going here, I have to give a plug for the Creation Research Society, since I am the new president. And I expect to see some real changes in the society in the future. And here's our new logo. Notice it says, research is our middle name. You don't hear much about the society because we don't build tourist attractions. We don't hold super duper mega colossal conferences. We don't make movies. We do research. So we have a research laboratory is just being built, finishing up. The CRS conference in July will be held there. We're expecting great things from this. We just got funding for an FTIR spectrometer, and Kevin Anderson, our lab director, can't wait to get his hands on that. He has refrigerators full of samples to be tested for our project. We're doing a study. He's doing a study on degradation of collagen over time. You probably have heard that they find dinosaur soft tissue now in bones. It's actually becoming quite common. Well, that's an obvious problem for the evolution, because how in the world can tissue be stable for 70 million years? And so they came up with a beginning model how they claim they can make that last longer. It has to do with dinosaur blood. Iron in dinosaur blood, they're claiming stabilize these molecules for a long time, but they never really tested that. And so Kevin Anderson is working on a serious, big study testing the degradation of collagen over time. That's why we need that spectrometer for. And so we're pretty sure we know what the end result's going to be. They're not going to be able to extend it the way they need it. And this is going to be data so good we can publish it elsewhere, not just Creation Research. The society also, we have a research conference where other scientists get together and discuss things, present preliminary ideas, and is not very well known. We have research grants available. As the new president, we're going to focus on that a lot more. I'm intending to have annual targeted grants for various scientific disciplines. Okay, comets. They're obviously a very beautiful thing. So here's Comet Not from 2007. I mean, just look at that. Just incredibly beautiful, isn't it? You can see the bright part there near the horizon. You see this tail coming up. You can see stars through the tail. Here's another view. You can see the tail really twisting. There's Comet Hailbot from 1997. And this clearly has two tails. Danny mentioned that the other day in his talk. Now, comets historically have been bad omens. The Emperor Ruzhong of the Tang Dynasty in China. A comet appeared in the sky, and he abdicated being emperor. He was a weak emperor anyway. They were pressing him for other things. But it was the comet was enough to convince him to give up the throne. Julius Caesar, sometime after he was assassinated, a comet appeared in the sky. And then his successor, Augustus, claimed, see, that's Julius Caesar's being accepted into heaven, the comet, the symbol of that. So you think of comets in ancient times, think of bad things happening. Another good example here. This is part of the Bayeux Tapestry in England. This is a very long thing. It goes meters. Where they have it in the museum, it goes around the room kind of like this. And this little section here has Halley's Comet in it. I have the arrow there. In this section of the tapestry is about the coronation of King Harold in 1066. The last time England was successfully invaded. And so comets are considered omens of bad things happening. In 1910, when Halley's Comet came around, that contributed to the unrest in China, and people were nervous about that. They expected bad things. That contributed to the Xinhai Revolution in 1911, which ended the Qing dynasty. Emperor Puyi abdicated the throne. Of course, he was like 6 at the time. And the Republic of China was born for a while. Okay, one thing people often wonder, was the Star of Bethlehem a comet? You see this in his painting by Giotto. And Giotto had seen a comet like a couple years before he painted this. Well, on the basis of what I've told you so far, comets are considered bad things. Do you think God would use something that people associate with bad to announce the Messiah? I really don't think so. If you want to know more about the Star of Bethlehem, Dan's got much better talks on this than I can tell you about. So I don't think it's that. The word comet itself is from Latin, meaning hairy star. To ancient people, anything that gave off light in the sky was a star of some kind. You had regular stars, then you had wandering stars, those are the planets, and you had Comets, hairy stars. Our English word disaster is based on dis and aster, bad and star. That shows you how deeply ingrained this idea was, even though they're very beautiful. Okay, people started thinking, what really are these things? Aristotle said, well, comets are part of the atmosphere. They're like lightning. Okay, then we really begin to understand things with Tycho Brahe. There's a painting of him in the 1500s. He was the best pre-telescope observational astronomer in the world. He had years and years of very high precision data. He invented instruments to make the measurements, which he passed on his measurements to Johannes Kepler, launching the Copernican revolution for real. Well, Tycho, when a comet came around, had observers placed at different locations to observe it, and from everyone he consulted, they were seeing the comet in the same place in the sky. If it was just in the atmosphere like lightning, it'd show up different background stars. So this showed the comets were actually in space. Also, Tycho figured out the comet tails point away from the sun. Then this guy, Edmund Halley, is not Haley. His family pronounces it Halley, like it rhymes with valley. In America, we didn't start saying Haley until a rock band in the 50s, Bill Haley and the Comets. Anyway, he was really interested in the study of gravity, and he began to wonder if comets, if they're in space, must have some kind of an orbit. So he figured some of these were periodical and they're coming. So he went through historical records, and he went to this guy. Want advice on how to analyze and figure out orbits. It turned out another astronomer had gone to Newton a few years before and asked him about the same thing. Newton worked out the physics and the math and never published it. He didn't like dealing with controversy or whatever, and people making fun of him. So basically, Halley showed up, asked him about this, and Newton's like, oh yeah, I've had this figured out years ago, pull out some drawer. And Halley's like, this guy's a genius. He got friends up putting up money and helped getting Newton published. Turns out Newton's method worked, and that was very influential because they could now take Newton's work his laws of physics, the law of gravity, his calculus, and the beginnings of perturbation theory. And they could predict what comets would do. That was incredibly powerful as a strong evidence that Newton was right. They could explain stuff in the sky they could not explain before. Well, so Halley had examined comets. He found out the comets seemed to be coming on a repeating cycle from like these years. And he came up with a 76-year orbit and predicted this same comet would come back in 1758. Unfortunately, he didn't live long enough. But if it came back in this year, he said it would. First prediction of a comet in modern times. Because of that, the comet is named after him. Okay. And so they had enough, they knew what they were looking for now. And so here's the orbit of Halley's Comet. Very elliptical. And then the different circles are for the orbits of Jupiter, Saturn, Uranus, and Neptune. Neptune's the farthest out. You know, the orbits of the planets are actually ellipses, but they're almost circles. Orbits of comets are very elliptical. They spend most of the time far from the sun and a little time close. And when the comet is close to the sun, that's when you get the exciting part. Since they now had good math and could predict the orbit, they could go back and look at other historical records. And so, as far as we can tell, the first historical record of Halley's Comet was done by Chinese astronomers in 240 BC. This record was already there, and they could work backwards when the previous times would be, and they would start tracking these down. In 684 AD, it came around. This was published in 1497. 1531, Halley's Comet again. Now that they knew what they were looking for, they could identify these comets that had already been seen. The first time Halley's Comet was really photographed was in 1910. Before then, they were just trying to make drawings as fast as they could. They had black and white film, very dramatic pictures here. Okay, Halley's Comet came around again in 86. And this is the first photograph when they first found it again in 82. This was cutting edge digital technology at the time. Your iPhone's probably better than this now. So that little dot there where the circle's around, the circle wasn't there when they did this. They caught it again, but this time they were ready for it when it came around 86. They got lots of photographs of this thing. And the bottom picture here, they're able to process digitally, looking at various levels of brightness in there. And you can see some structure in that simple photograph. And then the last time we saw Halley's Comet was in March 21 of 86. Here it is on its way back out to the orbit of Neptune nearly. It's not going to come back again until 2061. In North America, it wasn't easy to see. I managed to see it a couple of times in 86, but not very good. I'm not going to get another chance. I don't think I'm going to live that long. Okay. There's plenty of other comets. Halley's is very important historically. So this is the comet at KZhang. Comet names named after who found them. And so two guys found this, so they have the hyphen there between their names. But what they've done in this photograph, it's an animated GIF here, series of photographs. And the telescope was set so that it kept the head of the comet in the same position. And the computer would track. Look at the background stars. What are they doing? Notice the background stars, instead of being dots, they're like little lines. That's because it's a time-exposed photograph. and the stars are streaking there. But notice the stars are going down the photograph. What does that mean what the comet is doing? It's going up. And now look at the tail. Something down on the bottom right is pushing up on that gas and dust, pushing it out there like that. You can see stars through this. So it tells you what the tail's doing. It's not pointing along its trajectory. It's pointing away from the sun. Or here is Comet Schwarzman 3. I think the 3 in there is because it's like the third one these guys discovered. So May 2006. Here, you can see the comet coming down, but look at the background stars. They're moving from right to left, so it's not going in the same direction as the tail's pointing. It's like Tycho had found tails point away from the sun. Here's the comet tail. And when it's far from the sun, it doesn't have a tail. The tail starts getting brighter around, starts picking up, say, around the orbit of Mars as it comes in. And the closer it gets to the sun, the better the tail becomes. Side, back out in the deep space, tail goes away. Now, the structure of the comet itself, all comets are similar to this. So you got the nucleus there. A typical comet nucleus is like 10 kilometers, 15, in that range. It's not exactly a sphere. It's too small, so they look kind of like potatoes. And that's about 10 kilometers. And you look at that part in the blue there, you have the coma. And inside that is where the nucleus is. And the coma gets out about 1 million kilometers, and around that, you get a hydrogen envelope, and then the tail, both tails go out like 10 to the 8 kilometers or so. You have a dust tail or an ion tail. Now, the comet nucleus itself, like I said, looks kind of like a potato typically. Here's Hallies Comet. European Space Agency sent 3 spacecraft by it. Each one would get pictures, and so they had one spacecraft would get only so close, guaranteed they had some pictures. The next one would get a little closer and get as many pictures as it could. The Giotto probe was the closest one. And the picture of the nucleus of Halley's Comet is on the right there. As surprised as everybody how dark this is. And then our interpretation of the data there is the diagram on the left. It's kind of potato-like. It's got valleys, mountains, and it's spraying out gas. Here's another picture of the Halley's nucleus. And on the right, we've sent other probes since then. This is Comet Hartley 2. It looks like a bone. It's so small, gravity's not strong enough to pull it in tight. And this one's lighter in color. We've also sent spacecraft to actually land on these and get samples. Okay, let's say you have a nucleus of the comet, you have a coma. This is Comet Holmes in 2007. And they're able to get the nucleus in there, then you have to see the coma around it. What ends up happening is when the comet comes back close to the sun, say around Mars or so, in its orbit, it starts warming up. It gets hotter. Because it's warmer, the ice sublimes. Gas and dust are there, and that spreads out. Then the tail actually forms around Mars. You have 2 tails, and the gas tail I've heard referred to as the ion tail or even the plasma tail. All 3 mean basically the same. That is caused by the solar wind. The coma is spread out. The solar wind impacts on those gas and dust and pushes the gases out. And then the dust tail, the solar wind isn't impacting that because dust is a little bigger. It's the pressure of sunlight. And over time, that starts pushing these dust particles away. That's why there's 2 tails. gas tail from the solar wind, radiation pressure for the dust tail. And that understanding explains this picture, Comet Hailbop. The dust tail is white because it reflects sunlight, just scatters the light. The ion or gas or plasma tail, it gets ionized ultraviolet light, ionizes molecules like this, and they start giving off their own light. That's why it looks blue. Comet orbits are often very elliptical, and they often get away from the ecliptic, unlike the planets. Planets are close to the ecliptic. The ecliptic is the plane of the Earth's orbit relative to the sun. Okay, this is the Perseid meteor shower for Colorado one year. It took 40 different photographs in 2015 and then photoshopped them together. So you can see all these streaks as if they're coming from one location. The location they're coming from is, the appears they're coming from is called the radiant. And the constellation the radiant is in is how they named the meteor shower. So it's the Perseid meteor shower. So the radiant here is the constellation Perseids. Turns out we can explain these with comets. See, when the comet orbit gets near the Earth, look, it's going in its orbit there, like on the left. Well, every time it comes around, it's leaving little bits of stuff. And that goes in orbit around the sun as well. And that gets spread out over time. And when the Earth's orbit intersects that, those little fragments come in and you get a meteor shower. For Hallies Comet, since it's so prominent in our discussion today, when the comet would be coming up, that's ascending node, and the debris left in the orbit there, when it intersects Earth's orbit and Earth is there, it's Eta Aquarids in the constellation of Aquarius. When on the other side, the orbit goes down, it goes to the constellation of Orion, so it looks like the radiant is there. Okay, now this is the really important part. Okay, every time a comet goes around the sun, it loses mass. That's where the tail comes from. And so a comet will lose, 0.1% to 1% of its mass every time it goes around the sun. Well, the comet's only so big when it starts. How many times can it go around and still have ice left? Well, short period comets have been designated something less than 200 years in its period. At most, a short period comet, based on understanding right now, the most it can last is a couple of hundred orbits. Well, Halley's Comet's orbit is like 76 plus or minus 5, it varies, years. If it lasts a couple hundred orbits, how long can that have been there? Why do we still find short period comets if the solar system is billions of years old? Because evolutionists claim comets are leftovers from the formation of the solar system. We keep discovering new short period comets. We have better technology, computer searches, all that kind of thing. Okay. That's the data about comets. Interpretation time. Your worldview will dictate your interpretation. So if you have a non-Christian worldview, you would filter the data you get from the world through your worldview. So if you're convinced you see death, bloodshed, suffering, disease, millions of years, that's how man came to be. If you have a Christian worldview, you look at the same evidence and come to different conclusions. So you interpret things as creation, corruption, catastrophe, confusion, Christ, cross, and consummation. God's going to come back and fix everything. So it is possible two people to look at the same piece of evidence and come to two different conclusions. So the guy on the left has a biblical worldview. He looks at this skull of, I think it's a dinosaur, based on the number of holes in the head, and he says, wow, that's great evidence for creation. The other guy, who's convinced for Darwin's correct, looks at the same exact skull, says, wow, great evidence for evolution. It's like the way Dan Laeth put this same hardware, different operating systems. I'll let you decide which one's Mac, which one's PC. Well, the question was, how do you still have comets, short period comets, if the universe is billions of years old? Shouldn't you run out of them? Well, they're already convinced how the solar system formed. They're convinced comets are leftovers. There must be a comet bank of some kind that every so often sends new comets into the solar system. And so they've got the Kuiper Belt and Oort cloud. Kuiper Belt's close in, it's around the orbit of Neptune or so. Oort cloud's way, way out there. This is supposed to be leftovers from the formation of the solar system. Yeah, the Kuiper Belt. Objects are there. We found them. These objects made of ice and rock. They're nearly the orbit of the ecliptic. So from like 30 AUs, which is the orbit of Neptune, all the way out to, say, around 50 AUs. And we have found thousands of things there. And early detections were larger than comet nuclei. These objects are much bigger than 10 to 15 kilometers or so. And the aphelion, that's the farthest the comet gets away from the sun. Many comets have their orbits that go out that far. They're claiming the Kuiper Belt's kind of a bank for short period comets. And they found things there. So most of the ones we found are big. Since the early studies, they start sending more sensitive instruments looking for sizes. The biggest one is the easiest to find. That's not a surprise. It's easier to find an iceberg than a snowball. And so the statistics to describe this is a power law. So the horizontal axis has to do with size of the particles. And so on the left, see, is D. And so how many things you're finding at that diameter? The vertical axis is the number you're finding. Of course, the smaller ones, you're finding lots of those. Then like twice the diameter for the same volume as the second one. You have fewer of those. And finally, after 4D, same volume as all the other ones, you find very few really big ones. And you make a histogram of this and study that. Turns out this is the exponent describes this as 4. Pretty consistent. You find lots of you find very few big ones, lots and lots of small ones. You have the same exact situation. They first found exoplanets, planets around other stars. The first ones we found are the ones you would say are easier to find. The big ones that are close to the star. So lots of those first, then as techniques got better, start finding some, instead of Jupiter size, when you start finding like Neptune sizes, you're finding them farther out. Now we're up in a range with exoplanets, you're finding more and more closer to Earth size. You find the easiest to find are the big ones. The same thing here with the Kuiper Belt. The easiest ones to find is the big ones. It's harder to find the smaller ones, but there's more of the smaller ones. Okay, we do have short period comets, shorter than Hallies Comet, for example, how do you get a shorter period for a comet? So in the diagram here, so at 1, you have a comet coming in with a very highly elliptical orbit, and one time it gets in close to Jupiter or Saturn, where the gravity is very strong, and that can tweak the orbit. And it can actually bring it into a shorter period, closer to the sun. That's a complicated interaction. That's one way to do that. The Oort cloud. Okay. Long period comets supposedly come from here. And here's an example. Originally, I would have evidence for the Oort cloud. I had a blank page. But after my conversation with Danny last night at dinner, I knew I had to revise this. So I finished this at 5 a.m. this morning. I got a few hours sleep, got up, and worked as fast as I could. So if I word things a little odd, that's because I was kind of tired. Okay. This is a picture of UN 271, discovered in 2014. Short, other names like Bernardelli Bernstein. Okay. Its aphelion is out there in the range of the Oort cloud. And it shows evidence of outgassing, which is a key characteristic for comets. And so you could make the case that this thing is a comet which goes out to the Oort cloud. However, this thing's pretty big. It's like 10 times as big as your typical comet. Okay, so up until like yesterday, I was going to say you don't have any evidence of the Oort cloud. They're going to claim this is evidence of the Oort cloud. We have to think carefully. Now remember that power law distribution I was just telling you about? The biggest ones, like this, are the easiest ones to find. We're finding these. There may be a bunch of them a lot smaller, like maybe actual comet size. We're not sure yet. And so the implications of this, Oort cloud has some evidence. And so creationists need to reevaluate our argument of using comets as evidence of a young solar system. I didn't say throw it out yet. I said reevaluate. Before it was easy. No evidence for anything in the Oort cloud. Now they have some evidence. Further studies needed. Now, what it may mean is we're going to have to dig out the orbital mechanics, work through that, end up saying, okay, yeah, it just does work some, but, off the top of my head here, the rate of putting comets into the solar system is too small. You can't use that. It doesn't explain things. It might be something like that. Or you may end up with the other. Maybe it's too big. If it's as big as what you would need for the current rate of comets coming in, the early solar system would have plastered. We see evidence of that in cratering. I don't know. Further studies needed. Our work just got harder. Doesn't mean it's gone away. And the last thing here, we need more creationist astronomers. We have a good number of biologists and a good number of geologists. And you got enough people for critical mass. They can do some serious research and good model building. The number of creationist astronomers, Danny and I can count on 2 hands. That's not enough to really think things through. So if you know someone interested in this kind of thing, point them in our direction. We have plenty of work to do. Like Danny and I have been talking. This is about the comets and the creation model. We really don't have a creation model for the solar system, other than just saying God did it. We don't have a good model for stars. We don't have any model for galaxies. And of course, I was the one that got the question last night about galaxy simulation. I was like, that's way out of my field. We do have some beginnings of a coherent cosmology. We got 3 or 4 out there which are looking promising. Russ will tell you one of his latest one later. So that's as far as I got. The evidence of comets being evidence for a young solar system is probably still good. We may have to work harder to tweak things to make it clear. I don't think the star of Bethlehem was a comet. The other way it fits. Comets are significant in showing that Newton was right, which launched modern science. And of course, comets are incredibly beautiful. That's God's artwork.